Welcome to this explainer. Today we're tackling a massive, literally foundational topic, computer networks. Now, if you've ever felt completely overwhelmed by the sheer number of protocols, layers, and endless acronyms, well, you're absolutely not alone. But here's the secret to mastering all of it. You can actually think of the entire internet as a highly efficient global postal service. Seriously. Every single concept we're going to cover today maps perfectly onto how a physical package moves from a sender to a receiver. So, get comfortable and let's decode the internet together.
Okay, let's dive into this. Here's our mental map for today, which will perfectly structure your prep for any upcoming exams or technical interviews. We've got 5 parts. First, the network blueprint. Second, shaping the physical path. Third, IP addressing and subnetting. Fourth, transport and reliability. And finally, DHCP, the IP manager.
Let's jump right into part 1, the network blueprint. Now, every great postal service needs a blueprint, right? Standard operating procedures. Well, sending data is just like writing a letter. At the very top, you have the application layer. This is you deciding to write a message and sealing it in an envelope. As that message moves down the protocol stack, it gets formatted, tracked, and routed until it finally hits the physical layer at the bottom. And that layer, that represents the literal postman carrying your letter down the street via copper wires, fiber optics, or even wireless radio waves.
But in the real world, there are actually 2 main blueprints we look at, and interviewers absolutely love asking about this difference. On one hand, you have the OSI model. This is our theoretical 7-layer reference framework. It has these very strict boundaries, which makes it fantastic for learning and troubleshooting. But then you have the TCP IP model. This is the practical 5-layer system the internet actually uses every single day. It's a lot more streamlined, basically combining the top 3 OSI layers into a single application layer. So remembering that OSI is our theoretical reference, while TCP IP is what's literally running on your computer, is absolutely crucial.
So we have our overarching blueprint figured out. But if we're sending physical signals, how are the physical roads of our network actually laid out? Let's find out in Section 2, Shaping the Physical Path. Now, what's really interesting about the slide is how a network's topology represents the physical streets and intersections of our whole postal delivery analogy. And you'll frequently see the stark trade-offs between 2 classic layouts on exams, ring and bus. In a ring topology, devices connect in a circle. Data passes super neatly from one node to the next using a token, which beautifully avoids data collisions. But there's a massive catch. If just one single device or cable breaks, the entire network crashes. Boom, gone. Compare that to the bus topology. Here, every device taps into one single backbone cable. It's incredibly easy and cheap to install for small networks. But because everyone is sharing that one central road, heavy traffic almost always leads to data collisions, which slows the whole shebang down. Okay, so we've laid down the physical cables and roads, but roads are totally useless if you don't know where you're going, right? So how do we find the exact destination of our data? That brings us perfectly to Section 3, IP addressing and subnetting. Just like a physical house needs a zip code and a street address to receive mail, network devices require unique logical identifiers. We call these IP addresses. But as networks grow, managing thousands of these addresses in one giant pool becomes completely chaotic. So the solution? Subnetting. Basically, subnetting is the process of dividing a huge IP network into smaller logical subnetworks. Think of it exactly like a city planner taking a massive, sprawling metropolis and dividing it up into specific, manageable zip codes. We do this mathematically by literally borrowing bits from the host portion of the IP address and assigning them to the network portion. Now, you might be wondering, why go through all that mathematical hassle? Well, these are the exact benefits interviewers look for. First, it reduces broadcast traffic, so one noisy computer doesn't wake up the entire city, just its local neighborhood. Second, it drastically improves network security by isolating different departments. Third, it ensures really efficient IP address utilization so we aren't wasting precious addresses. And finally, it simplifies routing for the networking hardware. All right, so our package is perfectly addressed and on its way. But honestly, the internet is kind of a chaotic place. What happens if a package gets lost, dropped, or corrupted in transit? Let's explore that in Section 4, Transport and Reliability. Up at the transport layer, we have to make a crucial choice about our delivery service. Do we want it fast, or do we want it guaranteed? We basically have 2 brilliant methods for handling errors here. First, there's forward error correction, or FEC. Here, the sender attaches extra redundant math to the data, something like a Hamming code.
This is incredibly clever because it allows the receiver to detect and fix the error entirely on its own, no retransmission needed. This is absolutely vital for things like satellite communications, where asking for a resend just takes way too long. On the flip side, we have backward error correction. If the receiver spots a mistake here, it simply requests the sender to retransmit the data using a system called ARQ. It's highly reliable, for sure, but it definitely adds delay.
So the crucial point is how these concepts translate to the protocols we use every single day, TCP and UDP. TCP is connection-oriented. It's literally the registered mail of the internet. It guarantees your data will arrive perfectly in order, and it checks for errors. But that careful tracking means it has higher overhead and is, frankly, a bit slower. UDP, on the other hand, is connectionless. It's like a quick postcard just thrown in the mailbox. It's incredibly fast because there are no acknowledgments or error recoveries at all. If a packet drops during your live video stream, UDP doesn't care. It just moves on to the next one.
Now, because TCP guarantees that delivery, it actually has to politely introduce itself before sending anything. This is the famous TCP three-way handshake. Step 1. The client sends a SYN, or synchronized message, saying, "Hey, I'd like to connect." Step 2, the server replies with a SYN-ACK, basically acknowledging the request and saying, "I'm ready, let's connect." Step 3, the client sends a final ACK, acknowledging the server. Only after this super polite, three-step hello protocol exchange does the reliable data transfer actually begin. Okay, we've built an incredible system for routing and delivering data. But actually, scratch that. We missed something huge. Before any of this happens, how does a device get its IP address in the very first place? I mean, you didn't manually type one in when you connected to Wi-Fi today, right? Which leads us to our final part, Section 5, DHCP, the IP manager. You can think of DHCP as the local postmaster general of our network. It completely saves network admins from the nightmare of configuring IPs manually. And this brilliantly illustrates how a computer officially enters a network using the DORA process. First, discover. Your client device basically shouts into the void looking for a DHCP server. Second, offer. A server hears it and offers up an available IP address. Third, request. Your client officially requests to lease that specific offered IP. And finally, acknowledgement. The server finalizes the lease. You've got your IP, your subnet mask, and your default gateway, and boom, you are officially on the grid. But hang on, we've got a classic chicken and egg problem here. How on earth can a computer send that initial discover message over the network if it doesn't even have an IP address yet? Well, the workaround is absolutely genius. The host uses a reserved placeholder address, 0.0.0.0, as the sender. And for the destination, it uses 255.255.255.255, which is the local broadcast address. This essentially tells the network switches, look, I have no idea who I am, and I don't know where the server is, so please just blast this message to absolutely everyone. The DHCP server hears this broadcast and smoothly takes over. So, what does this all mean? We've covered a massive amount of ground today, right from theoretical blueprints down to physical topologies, IP addressing, reliable transport, and automated DHCP. But I want to leave you with a somewhat provocative thought. The IPv4 addressing system we unpacked today, it's practically out of unique addresses. As the Internet of Things brings literally billions of new devices online, how will the exhaustion of IPv4 force us to completely rethink these foundational delivery rules in the transition to IPv6? It's a huge, fascinating challenge for the next generation of network engineers. Anyway, thank you so much for joining me on this explainer. Keep asking questions, and I'll see you next time.